right, can everyone hear me? We'll get started so we don't run over time. A survey done earlier this year found that 77% of IT decision makers don't trust the data they use to make decisions. What's more than that, 91% of those respondents said they need to improve data quality in their organization. Now, how many of you here have ever dealt with data quality issues? In some sense, a bias sample because you did show up to the talk. But what these statistics up here and what we see here in this room really represent is the new reality today. Namely, that it's no longer a challenge of how big, diverse, or distributed your data is that you can't trust it. My name is Vicky ANDONOVA, and I'm a leader of the machine learning team at ANOMALO. ANOMALO is a data quality platform, and our main goal is to help companies trust the data they use to make decisions. Now, creating that trust, and more importantly, scaling it, is exactly what we'll talk about today. So I've spent the last 4 years thinking deeply about the problem of data quality, but it hasn't always been so top of mind. In fact, my first job in data was teaching young professionals as they made the switch into data science. And there, data quality just meant removing null values or imputing the mean, and all just a means to an end to move on and get the idea behind the algorithms and help students build intuition of how they work. It wasn't until I joined Instacart where I learned and really realized the impact that data quality can have, not just of the on the data team and the productivity and kind of effectiveness of the data team, but on the organization as a whole. Now, Instacart was unique at the time because, and sorry, for those of you who don't know, Instacart is a grocery delivery service. So think Uber Eats, but only for groceries. And it's probably the biggest one in the US right now. Now, Instacart was unique because decisions weren't just made based on data by running an experiment and analyzing and hoping to make a better outcome, being data informed. Data was really at the core of every single decision we made. From what we think will be in store when our shoppers go there because we didn't own the inventory, to who we think should go shop for it, who we should send there, how much it would cost, how long it would take them to shop for everything. Those were all data decisions. So when data quality degraded or became unreliable, it impacted our way to bring back revenue and grow as a company. I ended up spending a lot of time playing whack-a-mole with all these data quality issues, but nothing I was doing was really scaling. So that's what inspired me to join ANOMALO and join our co-founders as one of the first engineers and build a system that not only works for my team, my organization, my company, but works for all teams, all organizations, all companies. So today, we'll talk about data observability and data quality, what they are and how they're different. We'll define what effective data quality monitoring looks like. We'll look into 3 methods for data quality monitoring and zoom in specifically on an unsupervised machine learning example and the algorithm behind it that powers it. So you guys will also get some intuition behind the algorithm as well. So first, have any of you heard the terms data observability and data quality? Again, also bias sample, you all showed up here today. But the problem is that these terms are used interchangeably to mean the same thing, but they don't actually mean or even do the same thing. What data observability is the monitoring of how data is moving throughout your organization. Is it arriving? Is it arriving on time? Is it reliable, essentially? It usually involves monitoring some metadata and your pipelines. Now, makes sense. It's the absolute foundation. You need data in order to make decisions based on data. But most of you likely know it's not enough to have data to make better decisions. You need to have good quality data. That's why you need data quality monitoring as well. Now, data quality monitoring monitors the contents of the data that arrived. Now, it's great you have data that arrived reliably, but let's look at it. Let's make sure that this data meets our expectations. And that's probably the key here, the expectations. It usually requires some ML expert or data expert or a practitioner to define what the data should look like. Because of that, data quality is much harder to scale and maintain over time. Now, in reality, you need both of these to work together. But because you can imagine you can turn on data observability for your entire data warehouse in seconds. You're just monitoring the jobs and the pipelines. And data quality monitoring requires setting those expectations and scaling them. We're going to focus on this just because it's a bit harder to scale and how we can improve that process. So first, let's define what effective data quality monitoring looks like. To be effective, data quality monitoring must be easy. So it must be easy to set up the rules. It must be easy to execute what you want them to do. It must be interpretable. So when something fails, when an issue occurs, you should know exactly what to do to fix it. It must be scalable. You need to be able to scale to thousands of columns or billions of rows. And it must be sensitive. You need to be able to detect as small of a change that is meaningful for your team, for your organization. And finally, it must be comprehensive. So you can imagine you can set up thousands of rules for every single column, for every single one of your tables. But that still might not catch the unknown unknowns that are just things that you couldn't have conceived of happening, so you never set up a rule for it. So these are our 5 criteria for effective data quality monitoring. Let's look at some of the methods, maybe start with some of the more traditional ways that people do data quality monitoring. The first one is probably the most simple and straightforward one of those, and likely all of you are familiar with them. These are validation rules. These are hard and fast expectations you have of the data. So think a column is never null, a column is always unique, or maybe something, if you have some sort of noise in your data, maybe something like, well, I want my column to only be null up to 1% of the time. So these are great because they are very simple. Never null, always unique. You understand exactly what that check is trying to do. So when it fails, you also know exactly what it caught. But they require quite a bit of setup. So you need to tell them the table, the column or columns you care about, the type of rule you want to apply, and the constraint. Think never null or null up to 2% of the time. So what that means is not only do they take time to set up, but they also take time to maintain over time. So when, let's say, an issue or maybe just a product decision was made where null values just happen to occur more often in your data, now someone needs to go back in and change that 2% threshold to something that is more meaningful or okay for the organization at the time. So to improve on validation rules, we have what we call metric anomalies. Now these are your company KPIs that you're already likely tracking in some sort of BI tool across the organization. They're time series, they're aggregated over time. You need a table, you need the column or columns that they apply to, and you need a way to tell it how to define the metric you're looking for. Why do I say they improve on validation rules? It's because you don't need to set that constraint. Now that constraint is usually set up by some sort of prediction interval or confidence interval that is derived from that data and changes over time with that data as the trends change. Again, great because they're interpretable. You're very familiar with them already. You likely probably have some intuition about how they should move. But because of the way the threshold is set with confidence intervals and the way statistics works, when you scale these to thousands of tables, thousands of columns, you're still going to run into a lot of false positives. Now maybe let me pause here because we all know false positives are bad. Like you want less false positives, but false positives is really the biggest issue you should be looking for when looking to improve data quality. Why is that? When you have a false positive, that means, let's say we scaled these to thousands, maybe hundreds of thousands of tables. I now get alerts for hundreds or many hundreds of issues every single day. We know data people are limited resource. So over time, your data professionals will stop looking at those alerts because they don't know which ones are noise, which ones are real, and it takes time to discern between them. What that means is, again, over time, you have those professionals not only lose trust in the data and your whole organization losing trust in the data, but they're losing trust in the data quality monitoring system that you've now invested in and are trying to scale. So before we move on, let's see how these stack up on our 5 criteria. First, are they easy to set up? Not so much. You need to tell them a lot of things of exactly what you're looking for. Are they interpretable? Absolutely. These are great at this one. Are they scalable, as we just talked about? Not so much so. They require a lot of maintenance over time and a lot of manual setup. Sensitivity. This is probably where these 2 methods, especially validation rules, shine. So validation rules, if you have a rule that is column is never null, and even just one record is now null, it will catch that and it will alert you. Metric anomalies are a little less so here, but they usually have some sort of confidence interval, so you can play with that and get to a place where you're happy with it. But finally, are they comprehensive? Because they require me to input my beliefs of the data, they are limited by what my beliefs are. They're also limited by my experience of what I've seen happen to this data before. So these 2 are probably, their weakest spot is how comprehensive they are. Because of that, at ANOMALO, we've created a 3rd category here. This is our unsupervised data monitoring. If you can see, all this requires is a table you want to monitor. These are machine learning models that point at the table and learn what is normal of that table, and only alert you if the table deviates from that normal in the future. Now, they provide exhaustive validation with no setup, which sounds great, but they're not as sensitive as the other methods, and we'll talk a little bit about that as well. Now, it might sound too good to be true, like most AI machine learning applications are today, which is why I want to show you a little bit of what happens behind the scenes. So let's focus here. We'll take a look at an example, and here I have a set of ticket sales for different concerts or events. Now we can zoom in on one of these. This is a concert from The Who. It's happening in Houston, Texas, and yeah, it's categorized as pop. How many of you know who the heck The Who are? Yeah, that's what happens when you do this on this side of the pond. How many of those same people are a little offended that it's categorized as pop? Pretty much all of you. This is an American data set you'll see in 1 second. It's just everything, as long as it's a concert, it must be pop. So let's actually drill into the data. If we scroll down into the product, we'll see the column data types and the most common values. So you see how I didn't lie to you. If the category group is concerts, all the time it's a pop concert. What else could it possibly be, of course? If we go deeper into it, we'll go to our table homepage. So here you'll see the data observability sections. You see data freshness and data volume. Did new data arrive? Did all of that data arrive? Was it on time? And then in the bottom, you'll see key metrics and validation rules, which we talked about. So you can always supplement. You can get them all together. And finally, in the middle, these are unsupervised models that do all the monitoring on their own. You can see there's no way to add new ones. They all come out of the box. Now, how many of you have heard of the Netflix Chaos Monkey? A few of you. This is actually one of my favorite concepts. The Netflix Chaos Monkey is the system they use to make sure they build resilient systems in production. So the Chaos Monkey goes in and randomly shuts off different production instances. And this ensures that their engineers are building something that's resilient and scalable and won't go down if one instance goes down. At ANOMALO, we have the Chaos Llama, and as you may have guessed, it does something very similar. It goes into a data set and randomly introduces issues, data quality issues in the data. Now we have a library of different chaos, we call them chaos operations, that can happen on the data in order to introduce a data quality issue. And you can see there are hundreds of these. You can see some examples here. So think introducing null values, removing infrequent values, changing a specific value, things like that. And that's exactly what I'm going to do to our data today. I'm going to introduce some chaos. It's called the time column value chaos. It just means I'm changing a value in the data. I'm going to select our table. I'm going to select our column, the price per ticket column. One, because I love going to concerts and I hate spending a lot of money for them. So I'm going to say there's going to be a sale for $10 per concert ticket. I'm going to do that for 30% of records. And at the time I was in New York, so I want to try to go under the radar. I'm only going to do this for New York concerts. You also need to tell it when to inject it, so that's what you see here. And then we can go back to our table homepage and rerun that check. So you see everything has passed, all the validation rules and key metrics are good. We'll run this again. And you can see the check starting to execute. It's a little probably hard to see for you because it is for me too. But it starts querying the data, taking samples of different days. It starts building the main machine learning model, preparing the data for visualizations, and then finally generates all the dashboards.
What we were getting ourselves into.
If we go back to our homepage, we can see that the table anomalies check fails without ever knowing anything that I did to the data. You can actually see the validation rule. I set up something like that failed as well, but I needed to set it up myself. If we click into this, you can see that this is the headline of the check dashboard. You can see that it correctly identified that the price per ticket column, value 10, increased. You can see that this is categorized as a strong anomaly. It's way above the learned threshold. And what that learned threshold is, and remember this because we'll come back to it, is a threshold that is generated by the behavior of that particular table over time. So this is dynamic as well. So you will only get alerted if that table is more chaotic than usual. We can scroll down and look at the distribution of values. You can see indeed the value 10 increased. And then even down further, you can see a sample of the good rows and the bad rows. Now, this is probably as far as most systems will take you. And now as a data professional, I might take this blue dot and you can actually scrub through all the samples and squint a little and try to understand, well, okay, is there any pattern that I'm seeing here? Is something happening only for a specific segment or for specific geography? And if I was lucky, I would be able to stumble upon the fact that this has only happened in Venue City, New York. But if I was unlucky and I didn't think of that, or if there were many segments in the data to check, or if there are many cities in the world, it might take me days or even weeks, or I might never even get to it because priorities change and new issues arise. So this isn't quite enough. This is just identifying the issue. It's not letting me know how to fix it. This is my favorite feature of these models. This is the automated root cause analysis. So instead of me having to squint my eyes and find those patterns and then go to my SQL engine and start querying and try to see if my hypotheses are indeed right, this does that all for you. So it checks which columns or which segments in the data disproportionately are responsible for the anomaly. And you can see it identified that Venue State, New York, Venue City, New York City is the root cause of this issue. Again, without me ever telling it, hey, check out the mean of this column or monitor price per ticket and monitor price per ticket over these segments. So how did that algorithm find exactly what I did to the data without me ever telling it what to look for? Let's take a look behind the curtain. So the first thing we do in order to create this algorithm is take samples from today and yesterday. And we try to answer, ignore this for a second. We try to answer the question, is there material difference between the two samples? Did the data change in any ways? Is that an anomaly? Now, that's great. That's exactly what we look for in anomalies. But it's not quite a machine learning question. And this is where the key to all these algorithms really is. It's reframing the question into something that a machine can learn from. So instead of did the data change between today and yesterday, you can ask, can I predict for each record here if it came from today or from yesterday? That turns it into a machine learning problem. We now have a response column. From today is 1, yesterday is 0. And we auto-encode all the features you saw before into a feature matrix. And we auto-encode them because we are industry agnostic. Our models work for every single application you can think of. We work with financial data, healthcare data, social media data, anything you can think of. Now that we have our features and our response columns, we can build gradient boosted decision trees. You can see this is the model to the right, and you can see how it's learning over time. Now in this case, you can see that the log loss, the error of the model, goes down over time. So it continues to learn and is picking up some differences in the data. Of course, because there is that difference I created. You can imagine, on the other hand, if the model started learning and just flatlined up top, it's basically like picking up its hand saying, I don't know why you're asking me to do this. This makes no sense. There's absolutely no difference between the data. There's nothing to look for here. So it's telling you there's no anomaly for that day. So in this case, in the case where there is a difference, we actually drill down to those results and allocate to each column row combination for every single value in the data, how it contributed to that prediction. You can see this is the price per ticket column, that's more red there, and you can see the severity changes for different values that are closer to 10. Because of this, we are able to do these. We're able to explain in natural language exactly what is happening in your data. We're able to say that the price per ticket value 10 increased. We're able to tell you that the venue state New York is disproportionately responsible for this. Now, there's no free lunch. Of course, there are challenges to these approaches, and there are things that we had to account for. And if you're thinking of implementing something that's similar, you should think about these things as well. So first is seasonality. So we talked about taking a sample of yesterday and today and seeing if there's a difference. But let's say there's a change that happens every single Monday. So Monday will look anomalous compared to Sunday absolutely every week because there's some sort of seasonality in your data. So in fact, to account for that, we can't just build one model. We have to in practice, we build 4 models that take in different lookbacks in order to account for seasonality. There are also time-correlated features. Now, what feature will predict perfectly which date a row came from? Really any time column feature. So you need to identify those and remove them. But also there's a nuance to that. Think about ID columns that auto-increment through time. Every single day, your IDs will have higher value than the day before. So that will perfectly predict which date your data is coming from. So you need to systematically identify time-correlated features and remove them. Then there's also chaotic tables that are more inherently chaotic than others. Think a transactional database where there's just very cyclical user behavior versus a marketing data set where someone is manually going in and turning on and off different campaigns. The marketing data set is going to be much more chaotic and much harder to predict. That's where that learn threshold we talked about comes in. You need to dynamically set the threshold for each one of those tables to only ever alert if one is particularly chaotic on that day. Clustering across columns. So in data, there's rarely the case where an issue affects a single column in your table. What that means is you need to go in and cluster these anomaly scores and surface together every single issue so that it doesn't create alert fatigue and it doesn't overwhelm your teams. And performance, these must scale to billion rows and billion and thousands of columns, which is why we actually sample the data in order to be able to build these for any type of data. And finally, accuracy. This is probably the biggest issue with these columns because we sample. Because you sample, you can miss the needle in the haystack. So if you need to detect if just one value is wrong, this is not what you want to use. So let's quickly go through how these measure up. Are they easy? Absolutely. No setup required. Nothing you need to change. Interpretable. Because of the way we attach value to every single row-column combination, and we explain it, these algorithms are very interpretable. Are they scalable? We sample the data in order to scale these to any type of data you can think of. Sensitive, as I mentioned, this is the biggest Achilles heel of this approach. Because you're sampling, you can miss the long tail of changes. Good news is literally the simplest of all approaches, validation rules, is the best at this. So in practice, we tell users to turn these on for every single table in their data warehouse and supplement with validation rules and metrics for the tables they really care about, and they care about even a single value changing. And finally, comprehensive. Because I didn't need to tell it what to do, these algorithms are not limited by my creativity or my experience. These are able to catch unknown unknowns and anything that might happen in your data. And data inevitably changes over time. So these are able to detect everything that you can think of. So before wrapping up, I'd like to leave you with two thoughts. Think about the state of data quality at your organization today. If you're a data practitioner, how do you feel when you're asked to submit an analysis or deploy a new model for your organization? If you're a data executive, think about how you feel receiving those analyses or interpreting them. Are you tempted, if it doesn't align with your belief or your gut, to just go with your gut because the data has just been wrong before, so it might be wrong again? Now think about what it feels like to do the same things once you have these methods, looking for unknown unknowns, checking the observability of your data, making sure it arrives on time, and even checking every single value in the case of validation rules. Now, how do you feel sending that analysis? Or how do you feel receiving it? I hope this has made you excited about checking out tools like ours or even implementing something like this on your own. So if you have any questions, you can find me. We're at booth 732. Thank you so much.